If you're a backend developer, you should watch this video. I'm going to tell you a few tips and tricks which are very practical, which you should be implementing in your code base, in your infrastructure, in your application layer to scale your backend to hundreds of thousands of concurrent users, depending on what your application is using, and not crash under heavy load. So how does that happen? Let's take a look in this video. If you're new here, make sure you leave a like, subscribe to the channel and hit the bell icon. This is free of cost and helps the channel grow. Alright, so people usually talk about scaling their websites or their companies or whatever, but on a technical sense, all you have to do is always make sure that your backends are scalable. Your front ends never really come into the picture because front ends are fundamentally scalable, right? If you think about it, if your backend already has delivered something to the client is a small computer which has a small computation to do, but the server right here is the one which is bombarded by tens of thousands of computers simultaneously, right? So we are not going to be talking about how you write a good HTML, CSS, JavaScript thing because that's easy. Let's talk about the difficult part. How do you scale this guy right here so that it can handle a lot of connections simultaneously? Okay, so the first thing you have to realize is that you always want to scale your backends horizontally, right? Whenever you're adding a capacity, that should be a new server, right? It should not be vertical scaling because vertical scaling has physical limits. You cannot go beyond a certain number of RAMs and processing power and so on. But right here, when you scale horizontally in terms of creating more and more servers, you can assign them with more and more clients. So the clients per server actually comes down, and that is all that matters, right? This is a kind of a value which you want to control. You don't want to control the number of clients, obviously, because more the better, but you want to increase the server so that this ratio comes down. Now, this is the very fundamental part of backend scaling, but the fact that you have to do this gives you a few constraints to play with. The first constraint here is that your code should be stateless. The application layer of your backend, which is the layer, the business layer, which your clients interact with, the first layer, which is running on this backend as a Node process, as a Python process, as a Java process, as any process, that process could not contain state. By state, what I mean is, let's say you are doing some sort of authentication and you are storing the connected clients or clients which are last active in an array inside of your code, right? This is a disaster because if you do horizontal scaling, this server would create a fresh copy, and the way scaling works, these servers are assigned randomly to clients depending on what the load is currently. And if you're assigning a wrong server to the wrong client every single time, your client would just have a lot of hard time in terms of authenticating properly. So for example, if you're using some sort of authentication and matching it with a key value inside local state, that's wrong. You have to move your state somewhere central, right? Now what that central could be? That central could be a Redis store, or that central could be a actual database like MongoDB or MySQL. So once you do that, you have to just make sure that this horizontal scalability is present. Now, this is easier in some cases if you're using, for example, Lambdas at AWS. Lambdas can automatically horizontally scale till the limit you have specified, right? And it will just automatically shrink as well, and you will only pay the cost while your code is executing. So that's the beautiful part. You can also do this manually if you're using, for example, AWS auto scaling groups and stuff where you're running 8 EC2 instances and doing it yourself. The auto scaling group part would probably be cheaper for you if you receive a lot of traffic, but for anything which is like a few thousand users to a few 10,000 users, I think just going the Lambda route is better. Alright, so your application layer now is scalable, of course, thanks to Lambdas and horizontal scaling and stateless code. But what about this thing where you move the central dependency, right? The Redis and MongoDB, let's assume, this is still vulnerable, right? So one thing right here in terms of databases, let's talk about MongoDB first, is that you can use a distributed database. Now this is something which is getting popular these days a bit. So for example, FaunaDB, these databases, or I think PlanetScale is also one I have heard about. I haven't really used it, but PlanetScale database, these sort of databases, what they do is they expose your database over an HTTP server and they manage the internal scaling and read writes and everything on their own. Now with databases, the interesting part is that even though you can scale the compute all over the world, if you want to scale the database all over the world, you will lose out on things like strong consistency. If you want strong consistency, then you would lose out on things like performance. So it's a close competition between performance and consistency and what should come before, what you should optimize for. But the idea is that you should not really think a lot about, at least in the initial stages, as long as you're picking a scalable system. So FaunaDB, PlanetScaleDB, these are kind of some new choices which might not be very applicable for companies who already have existing databases. But even for MongoDB and MySQL, or anything which requires some SQL based database, I think there are options where you can use managed version of those databases. For example, MongoDB has an Atlas as a database, which is beautiful in the sense that you just boot up that MongoDB instance on the Atlas. It costs you a lot, like it starts with a $60 per month plan, which is production grade, but I mean, it's worth it because you don't have the headache to manage all the backups and making sure that your databases are healthy, your cluster is healthy, and so on. So managed database is also a great option. AWS provides a lot of services around this as well. Aurora DB, DynamoDB, and so on. So you can pretty much just go ahead and stick with some managed database as well to scale this. And for Redis as well, again, I would stick with the managed database thing where you have Elasticache and stuff which you control with the GUI. I mean, the fact is that you can hypothetically and technically, not really hypothetically, you can create these managed services on your own, but it's just not worth your developer time, right? Your developer time is more suited on this application layer right here, writing the actual code for this instead of worrying about the infrastructure scaling, the management, and so on. So this is the boring part, and this would actually reduce a lot of cost. It will actually make sense for you when you are a huge company, right? When you are actually trying to just optimize a lot of cost factors and so on. If you are a small team, a startup getting to product market fit, pre-PMF, you don't have a lot of traffic, or if you're trying to scale, you're even post-PMF, but you still have manageable amount of traffic, not a lot of bandwidth is going on, I think this infrastructure, this scalability is good for you. Then another tip which I have is always try to use managed, like we already discussed managed database, but also try to use managed services. For example, always prefer S3 over storing files on your own, right? Always try to prefer Lambdas, I would say, compared to just building your own upscaling, downscaling service, or even using, I mean, AWS obviously provides things like Fargate for Dockers and stuff, but try to use managed services. They make your task a bit easier, and if it is a cheaper service, then it is most likely a lot scalable, and if it is cheaper and managed, it's most likely probably like built for scale, right? So yeah, these were my 2-3 tips, 2-3 important things you should keep in mind when you're trying to design a backend that needs to be scaled. The stateless part is super important. Once you get that management, that managed services part is relatively easier, right? But your application layer should be stateless for the reasons mentioned earlier. A lot of people talk about how you can code a website, and a lot of tutorials talk about that, but usually they end there. In this video, I want to take a step further and tell you about some important things which you should know as a developer in order to deploy a website to your servers in production as a developer. Let's go. So for the sake of simplicity, let's assume you're just building a simple Create React app project with a Node.js backend, a standard MERN stack application, right? Let's assume you're doing that. Now, the first thing you will do is, of course, code up the application, which is your client here. And the second thing you will have is your server here, right? And most tutorials will actually end up here, where they just show you how to connect a client and a server and how you can run it on localhost port 3000. And that's it. Maybe you connect to a localhost port 8000 where your API server is running, but that's it. Now, how do you take this setup to the production, and what are the best practices? Let's discuss that in this video. So the very first thing you have to do is you have to create a repository to store your code on the cloud. Now, why you want to do that? You want to do that because, first of all, your system, your laptop is temporary, kind of. If you just smash your laptop on the wall, you don't want your website to be just vanished forever, right? Because if you cannot access your server, or if you cannot access your code, or even if you're working in a team, you want a central place to be the one where your code is stored and managed and maintained. So what you want as the first process is you want to push this on the cloud somehow, and the most popular solution for working with code is using Git. And here also you can choose from GitHub, GitLab. There are a lot of players, but usually a lot of people do prefer GitHub. Now the next thing is that you assign a specific branch here. In our case, I can just call it master. If you're not familiar with Git, make sure you check out this course on codedamn on how you can work with Git in general. But if you check out this branch master right here, this master or main branch, as some people have started calling it now, this branch right here has a special meaning. Usually, I mean, you can keep any branch as such, that when deployed to this branch right here, it goes directly to your server. Now, how does that happen? That happens because there is a process known as CI/CD. Continuous integration and continuous deployment. Now CI/CD, these are nothing but actually cloud computers. For example, for GitHub, we have something known as GitHub Actions. So these are cloud computers which build your code in production mode and also deploy it on the server. So what do I mean by this? Let's say you push your code on Git on, let's say, a branch called dev, right? You have a CI/CD YAML file set up which spins up CI/CD server, which builds your code, right? So it builds your code, that's it. That builds it for the production release. Because on the dev servers, on the development, you will not be really building production releases because it's slow and it's unnecessary and you don't want a prod release to be running on a dev server. So once this is done, what this server needs to do depends on how your production environment is looking. For some people, it might be just a simple EC2 server, right? You connect this to SSH, this is one way, or you connect this via git push. So you actually initialize a git repository here and push it from here. And the second step is you restart the server itself, right? So restart or reload or whatever you want to do. So this is the flow. You push it to a git repository, the CI/CD process run. It builds the server somehow, whatever the steps are. It SSH or git push or, runs a custom action. For example, in case of Vercel runs a custom action. So custom bot or action on your hosting provider, and it makes that build live on the production. Now this much flow would definitely help you get started, but what you ideally need is a flow where you route this traffic not from master but from a staging environment. So let's say you have a staging build where you run this CI/CD, and this CI/CD also contains a bunch of tests, right? So these tests actually run on a staging build. So once the CI/CD succeeds, let's say you have a special staging place, right? Then you run the test, then the tests succeed. So let's say these tests succeed, and then you merge it into master, or you just directly deploy it on prod, right? So what you're doing here is you push it to a branch, it builds, it runs the test on that staging environment itself. Now these tests could be end-to-end, they could be unit test or integration test, whatever you want. For unit and integration tests, it's relatively simple. For end-to-end, you have to build a complete environment and publish it, most likely on a live URL somewhere, and then run the test, but it is definitely possible. Finally, if you're deploying this on prod, if you're using a managed service like Vercel or Netlify or anything else which manages the service for you, you're good enough. But if you're using something like an EC2 instance or some way where you are using a server on your own, then you have to take care of the usual stuff like reloading instead of restarting the application. Why? Because you don't want to lose the existing connected clients. Second of all, maybe you want to follow a blue-green deployment pattern, which is some people like, some people don't like. You should ideally have a reverse proxy set up in front of your servers. You should have the standard web security in place, rate limiting, not trusting user data, and so on. And you should finally have checks on your service from external provider, which emails you or send you a phone, SMS, or some sort of notification if your service is down, right? This is like important because you want to know when your server crashes, not if, when it happens. Because if you're running on a single server, chances are sometime down the line you would either run out of disk space, or you would sometime be a victim of some sort of attack which will consume your RAM or CPU, so you want to be aware about that. But in other cases, if you're using a managed service, it's relatively less common, but still you should be aware about these things. So yeah, that's pretty much it. I think the most important part here is setting up this flow via Git and then via CI/CD and then via deployment. Once you get these three things right, all you have to do is enhancement over these three, including the test here, including some checks here, maybe including some flow here. But these three flows are, I think, the most important to get right. And if you don't have any experience with CI/CD, I would suggest starting with GitHub Actions. It's a natively built-in feature into GitHub and can help you just kickstart your continuous integration and development experience for the first time. This is not your regular Node.js tutorial. So if you're somebody who's new, just take a break, bro. Skip this video. I'm just kidding. You can stay and take a look. I'll see what I can do in order to help you understand a few important advanced things of Node.js, starting with what exactly happens when you try to do something asynchronous and how Node.js is not really a single-threaded programming language. Let's go. Okay, so this video is not for weak-hearted because we will be diving deep into operating system fundamentals as well a little bit in order to understand what is happening. So let's understand about operating system. This is Windows, Mac, Linux, whatever you're running. Usually these operating systems, what they come up with is something known as a scheduler. Now the scheduler has one job. Its job is to allow certain processes to run on these 1, 2, 3, 4 cores of the system, right? Let's assume you have 4 cores on your system and you have Mac OS, right? It doesn't matter, but 4 cores, Mac OS, the scheduler right here, what it is doing is that it is picking from all the processes which are trying to run on your system. Let's say there are 20 processes. So it's trying to pick a single process, let's say P2, and trying to schedule the threads of that process on the 4 cores of the system. Let's say this P2 process is actually in fact Node.js process, right? Now, the fun part happens when you use an asynchronous library which can work on something known as libuv. Now stay with me here. What do I mean by that? Node.js, not really a programming language, a runtime. People get very upset when I say that it's a programming language, but let's get the facts straight. It is a runtime which sits on top of V8, right? And V8 also, in case of Node.js on server side, uses something known as libuv. If that is not clear, this is a V. So this libuv is basically a component just like V8, which is responsible for everything asynchronous in Node.js, right? So the asynchronous nature of Node comes from libuv, and these are separate components, right? This library is not present when you're running JavaScript inside browsers, but that is still asynchronous because it uses something else. But the fact remains the same, that you need asynchronous behavior in Node.js, and that's what libuv gives you. Now, let's take a look at a function like bcrypt, for example. Bcrypt is a hashing function. That means it takes a single value, which might be very long, and spits out some random gibberish value, which is the hash of this particular value, right? It's used most commonly in password hashing for storing hashes of password instead of plain text password. But the fun thing about this is that this library, if you install it via npm install bcrypt, this installs a C++ binary, which is available to Node.js, right? Now this binary right here is asynchronous and can use this libuv to speed up a lot of computation. Let's take a look at how that does it. Let's say you have an HTTP server which is responsible for logging in people, right? And which uses bcrypt as a function call on the /login route. Let's say you suddenly have 500 people hitting the same route, and Node.js, being asynchronous in nature, can very well handle that. So the way it will work is that you would simultaneously have 500 calls to this bcrypt function, right? Which returns you a promise after processing everything. So what's happening right here on the first call, let's take a look at the first call. This function runs with the hashing and everything, and this does not return. Obviously, this returns you a promise which you await on. But the way this is working internally is that, like I said, I told you there is a C++ base library. So Node.js says that, hey, I don't know how to use this. I cannot call this because this is not a JavaScript code. Let me just ask the C++ guys, right? So it goes to the C++ binary. C++ says that, hey, I know how to execute it, but I could perform it in a much better way if I use libuv as well, right? Because of the asynchronous nature, because the library is asynchronous. So what this C++ does is that it goes to libuv and it says that I need to execute this bcrypt call, whatever it is inside of this. Now the fun part begins again, that libuv actually comes with something known as a thread pool, right? This thread pool right here is most likely, let's assume this is a collection of 4 threads, which is like a pool. It's not really executing in the system, but it's just a place, right? So libuv would say that, sure, I would place this in the thread pool, right? And once the process is available for the Node.js, we'll start executing it. So we go and store this in the thread pool. But remember, we have 500 or 499 more requests coming in, right? So the second request hit, the same thing happens. It goes to C++, C++ goes to libuv, and libuv adds it here in the second block, right? Similar thing for 3 and 4 as well. And that's it. That means the block is now, the thread pool is now filled. For the rest of 496 calls which are coming on the server, the bcrypt calls, the thread pool, the libuv just puts it in a queue, right? That, hey, let's just go ahead and wait because there is already a lot of stuff going on in thread pool, right? The thread pool is complete. Now, what happens is the moment we get the P2 process running in the operating system by the scheduler, the moment this happens, Node.js becomes active. And what libuv does is that it says to your operating system, hey, I have 4 threads which can be executed. Let's just go ahead and do that. So what thread pool does is that it throws every single one of these computation operations in their own dedicated cores, executing parallelly. Not concurrently, parallelly. So you have these 4 values right here, which are executing parallelly. So this means that you are computing your computer. This is actually 4 separate cores. This would compute parallelly, and they would, once they return all of that information, it goes back to thread pool. libuv, v8, basically get back to the Node.js world instantaneously, right? So if every single call of bcrypt takes 1 second, this process of computing 4 calls would also take 1 second because all of them are happening parallelly, right? Now again, of the 496 calls which you have here, they would be scheduled, and once any single one of them gets out in terms of getting the results, if this one evaluates faster, this gets out, and you end up with one block here which can be sent right here in order to execute, right? So then you have 495, 494, and so on, going all the way to 0. Now, a couple of observations which you would have made, that the thread pool size ideally should be equal to the number of cores on the system, right? Because if this is smaller, then you're wasting potential. And if this is larger, then you are actively pretty much just doing context switching here, right? It would start sending it here, but your scheduler would start context switching between the threads. And once that happens, things usually slow down because context switching also has its own time. Therefore, what you want is you want your thread pool size to be equal to the number of cores which you have on your system. And how do you set this thread pool size? There's an environment variable called uv underscore thread thread pool underscore size. So this variable, this environment variable, once this is set, that's what the libuv uses as the thread pool size. This is something someone asked me in the comment section the other day, which I already have created a video on in the advanced JavaScript course last year, but I still decided to do this because we have a new whiteboard format, so why not use that? So in order to understand a little bit of architecture, what happens is that this is your client. Again, this is something which we discuss all the time. And this is your server, right? Whatever your server sends to your client, index.html, XYZ, whatever it is, more scripts, this gets executed on the client side, right? So technically, even if there is something wrong, some sort of virus or anything, or, if this computer is on fire or something is happening, you don't care, right? You just say that, hey, this is my job. I just sent you something, and whatever you do, you blow up your computer with that, that's fine by me. But the way web works is that this computer can communicate with this backend as well. And this backend right here is a trusted source. You trust it with all your heart. Why? Because your database, which is connected, which contains all the sensitive secrets and stuff, has most likely unlimited access to the information, which is the case with most of the applications. Until you are, Facebook level, then you have segregation access even for the backend APIs. But the idea is that you don't want this server to be compromised. So as a job of a backend developer, you have to be extremely paranoid about web security. As a front-end developer, you can pretty much ship anything you want here. It would not affect you, but as a backend developer, it is your job to make super solid security measures so that this payload right here never really crashes, corrupts, does anything which you don't want to your database or to your application layer as well. Okay, so with that being said, let's also understand what is this payload right here and how you can work with it in a safe way. Here are my 4-5 tips. Let's see how many there are. So this payload is any information which this client sends to the server. Some of the ways is, the standard HTTP methods, post, put, patch, and using them, you can get them in headers, or for these methods, you can have something like body, content inside body, or you can upload a file, which is again, technically content inside body, but with different content type, right? So what you want to do as a first level of security is that you always want to check the size of the payload you are receiving. And ideally, this should be configured on the reverse proxy which you have, or if you're using a managed service, then it should most likely be taken care of. But you should want to restrict the size to a certain sane limit, right? Let's say you are creating a form which accepts a contact message, right? Then of course you don't want this message, or you don't want this input field, let's say, which is upload file, to be more than 2 or 3 MBs, right? Because let's say if you're storing this, if you're not even using S3 or anything similar, and you store this on your server with your other files, there's a high possibility someone can just crash your server by uploading a 50 GB file here, and you will just process the complete upload, and that's it. Your server goes boom. So making sure the size of the payload is in limits is an important factor to consider as a paranoid backend developer. Then once you cover the very broader sense of the payload, you want to go a little bit deep into the payload and try to figure out the type of the payload. Now this is an area where a lot of injections and stuff can arrive if you're not right, especially in the NoSQL world. You can have a lot of NoSQL injections. And what do I mean by that? Let's say you have a query for NoSQL which runs something like db.query, and then you have a is equal to request.body.name, right? So I'm not able to write it completely, but the idea is that this thing right here, you're expecting, let's say this is not name, this is name as a field inside of the NoSQL database. Now, if you're not checking the type of this request.body, it might very well be possible that somebody, instead of passing this as a string, pass this as an object. So the query becomes name, something like not equal to, and then 1, for example, and this would pretty much list all the people with a name not equal to 1, whereas you never really want that to happen. So it's like a classic case of NoSQL injection. So you don't want that. How you can fix that is actually make sure the types of the body you are requesting are actually what you expect as well. So a handy library for this which I can recommend is Joey. So Joey is a package which can help you with writing schemas for the data you want to accept and then execute them automatically, instead of just doing a manual if, type of, and stuff like this, which gets cumbersome and boring super quick. So Joey is what you want to use. The third one is contents of the payload, which is again more relevant for SQL injection rather than NoSQL ones. So contents of the payload just means that, for example, select star from blah blah blah, where name is equal to whatever your body is, right? So you don't want to do this. Why? Because somebody can just insert a single quote write a SQL statement and comment out the rest. Classic SQL attack. So you don't want this to happen. What you want is you want to inspect the contents as well in these cases, escape it, do whatever you want, or in this case, in this specific case, at least you should build the queries yourself, you know, using the query builder and any other safety measure included in the language. So introspect the contents of the query and don't just randomly pass user input without actually knowing a lot more information about the user input. What is the type, what is the size, what is the content, and so on. Number 4 is rate limit. So it might be possible that you have an expensive CPU intensive endpoint which the user can exploit. So let's say you have an endpoint which spikes your CPU usage with 2% for, I don't know, like 2 seconds, right? Maybe you're taking a screenshot of a website at this endpoint. So what somebody can do if this endpoint is not rate limited is they can just constantly DOS it with a very simple script written on their computer and bring your server, you know, to 80 to 90% usage, which might affect experience for other people on your server, right? So you don't want this to happen. So always try to rate limit your API endpoints. This is like, again, in the super basic things, just like we have size of payload, you should also have a rate limit set on every single API endpoint you have, at least for public. The 5th one is encryption of sensitive data. So if you're doing anything that even remotely, if it involves the use of credit cards or, you know, passwords or anything which neither should you know or somebody else know, then you should store this information very carefully. At least for passwords, you don't even have to just encrypt them, you can just hash them, right? So for example, for passwords, one of the good libraries is bcrypt. So bcrypt is a hashing algorithm as well as available as a standalone library, which just takes your input, which could be any sort of length, and just spits out some random garbage stuff. The good thing about this garbage stuff is that although this is random, this cannot be used to derive the original password. So what does this mean? In case your database ever gets hacked or gets leaked or somebody sees it, they can see all the public information, but they would not be able to see the passwords, right? So this is like super duper important that you have the proper encryption wherever you are using this sensitive data. And the 6th one is ports and services. By ports and services, what I mean is that only expose the things on internet which absolutely needs to be on internet. You absolutely never really want to expose as much as you want on internet. In most cases, what you want is just expose port 80 and 443 on your server, right? You never really want the MongoDB sitting on 27017 or the Redis sitting on some port number, Memcache sitting on some port number to be exposed on internet. Bare minimum services should be made available, and most of them, and if not all of them, should also be routed with a reverse proxy, because a reverse proxy allows you to add a lot of these things, rate limiting, for example, size of payload as well. All these checks in languages like C and C++ if you're using, I mean, you don't have to necessarily write C and C++. The code would be executed very fast. It's compiled to your machine code, you know, the native code, and this is like a battle tested software if you're using Nginx or HA proxy as well. So make sure you also follow these practices of having least possible services exposed on internet. On intranet or on VPC, that's fine, but on internet, make sure that you don't expose more than what's needed. And the 7th one and the final one, which I can think, at least for now, is disabling introspection. Now, what happens is, at least for what I know for tools like GraphQL and Firebase or Supabase or tools like these, what they allow is they allow people to introspect their endpoints. What is introspection? Introspection is a practice where the end client can provide auto completions or some additional smart features, but in return, your server actually pretty much sends them all the available information it has, all the available metadata it has for a particular thing. For example, GraphQL sends the full schema structure, more or less. If you ever visited localhost, you know, if it is running on localhost and /GraphQL, you would see that the graphical interface which it shows allows you to do auto completion, and it very nicely completes it. But if you ever ship that on production, that pretty much means everyone knows all the queries, all the mutations, all the resolvers which you have. This thing is more about security by obscurity, which is not good, but this is important. Security by obscurity should not be your primary method of defense, but definitely once you have followed these 6, also make it impossible for attackers, or at least very hard for attackers to discover what are exactly some of the maybe vulnerable endpoints at your end, right? So disable introspection on your GraphQL layer, on your REST layer if you're using any sort of framework, on your database layer if you're using these Firebase, Supabase, these databases. So make sure you do that. Webhooks is that one thing which I think a lot of people should know about, but they don't, and they just copy paste code to accept, let's say, a webhook call from a provider and be done with that. But in this video, I want to talk a little bit about it. What is a webhook? How you can create one, the process which is involved, and how it should ideally work. Let's go. So if you have ever accepted payments from Stripe or Razorpay or any of these payment gateways, you would know that there is a concept of webhooks from these payment providers, and payment is like the first example which comes to my mind because that's what we use extensively. But webhooks are everywhere. You will find webhooks on Slack, Discord, this and that, pretty much anywhere where your service wants to coordinate with an external service. So what webhook essentially is, in very simple terms, if this is your server, if this is an EC2 instance which you own, and this is like company like Stripe, for example, you can tell Stripe, hey Stripe, can you send a request to my server when something happens here, right? Now this something is basically called as that webhook event. In case of Stripe, for example, at codedamn, what we do is that when you buy the pro subscription or the full stack learning path or any learning path or any course, when you're on the Stripe checkout page, you will see the information to enter your card details and name and address or whatever it is, and then, you know, a payment button. So when you click that payment button, and when you enter all these details and your transaction is successful, Stripe under the hood sends a request to our Lambda, which is our GraphQL backend, and tells us that, hey, someone has paid for this service, right? Whatever it is. And it includes some metadata over here in this request. Now we, at our backend, we try to decode this metadata and get the user who made the payment and add the subscription to their account, right? And all of this is happening in a matter of seconds, right? You press this button, Stripe authorizes the transaction, sees if your card is valid and anything, charges your card, makes this webhook call, it sends us to our backend, we do this, and you get a pro account on codedamn. Now you would say that, hey, what about when Stripe redirects you back to your website, right? Stripe can give you a URL or something like the payment ID and this and that. Then you can use this to verify your transaction. Sure, but in this case, maybe this transaction happens and suddenly the electricity at your house just goes off, right? So the next page is you see, you know, declined or something. Or maybe this transaction does happen, but you close your browser by mistake, something like that. So these things could happen, or your internet stops working, or maybe codedamm's main website goes down, for example, and our webhooks are working, or even if they're not working, there is a way, we'll discuss that. But a lot could happen wrong if you rely on the client to provide you the information. And sometimes it is not even possible. For example, if I have a webhook configured in Stripe to say that, hey, tell me whenever the subscription is cancelled for a person. Now there are synchronous and asynchronous ways this could be called. A synchronous way is that you as a user actually go to your codedamn dashboard in your settings and click on the cancel subscription button. That is synchronous. An asynchronous way is that your payment, your recurring payment fails. In that case, Stripe would automatically call this for us to update our backend that, hey, your pro membership is over. Maybe we'll send you some information on email and so on. Now, a very important part here, a very, very critical part over here is that how does this backend knows that this request over here is coming from Stripe and not from an attacker or someone else. Now, this is a part where it gets interesting. So what we do, let's say if this is Stripe and this is our server, what we do at Stripe, first of all, is that we give Stripe a secret, or Stripe gives us a secret. I mean, you have to find this in a dashboard, in your dashboard. And what the secret is that it's a signing secret. So the way this works is that whatever Stripe is saying to me, obviously that is over HTTPS. That is like the first level of security. But the second level of security is that the message which is being sent by Stripe, I can actually validate whether that message is actually coming from Stripe server or not. How? The way I can do that is Stripe would actually attach the hash of this message. You know, we have talked about hashes, and I think we have talked about hashes, MD5 and SHA1. Let me know if we haven't, I can create a video on that. But a hash is simply, for a simple definition, I could say a hash is a one-way compression of data in such a way, not exactly compression. You can think of, for example, if I hash a 2 MB or 2 GB file, I'll get a string of 32 characters in MD5, which is pretty much more than enough to ensure the integrity of this file. So that means if anything, even a single bit is changed in this file, this hash would completely change, right? It's more like a signature. It's more like you don't have to parse the full file on a different source to know if the file is corrupted or not, right? You can just take the hash of that file on that other source as well. And if the string you get matches the string which you saw on the source, that means the file is fine. Similarly, what Stripe would do is it will hash this message over here and it will use our secret key here somehow. Why? Because this message which is hashed with our secret key, only I would be able to hash this message again, which is delivered in the body with my secret key, because this is something which Stripe and I have, you know, agreed on. And then I can verify if the hash signature, they usually send it something like X signature or X verification something, which is like a string of characters. If this thing actually matches the hash which I have generated at my end. So this part over here is, I would say, probably the most important thing. Why? Because if this does not exist, anyone could, if they are able to determine what the backend URL is, they could send a request and pretty much get a pro account or get a lifetime pro subscription or do anything they want. And if you're skipping this part, trust me, you're doing a big mistake. It's just a matter of time. If your service gets really popular, that somebody discovers your backend URL and starts spamming it, right? So what you have to do, first of all, is set up a webhook like this, where it is triggered by some sort of events, whether that's synchronous or asynchronous. And then it is having a capability of verification as well. So this is how Stripe works. This is how Razorpay works. This is how most good webhooks work and webhook implementations should work. At the end of the day, you would see that webhook is nothing but a server calling another server in a secure manner, right? Which is basically HTTPS, which is like the base security, plus signing the message. That's all you need to do. If you sign the message, if it is delivered over HTTPS, if you have the correct webhook URLs set up, it's actually a great way to actually listen for important events. One more thing you can establish as a webhook provider is that if your webhook server, if the endpoint actually gives you any status code greater than 400, for example, greater than equal to 400, which means, you know, either 404 or 503 or 502 not found, something happened, it tries the endpoint again, right? And the way it tries it is with an exponential backoff algorithm. I don't want to get into a lot of details, but just understand it will try, let's say this request fails. The next request will happen after 1 second. The next request would happen after 2 seconds, then 4 seconds, then 8 seconds, and so on, right? This is like an exponential backoff thing, because Stripe does not want to bombard your server if it is already overloaded. So it just backs off exponentially. But yeah, I mean, that's more on a reliability side of thing and a nice feature to have in a webhook system. But the core of the webhook is having this encryption in place and the ability to add events and dispatch it to different providers. Now, I have given an example of Stripe overall in this one, but this pretty much exists for any other system as well. So the next time you are implementing some sort of webhook functionality, you know why you need that, because clients are unreliable. Why you need to verify the signature, because you know security is important, and you know a basic understanding of how it is actually working under the hood. Even if you're trying to implement your own webhook functionality, all you have to do is give people the ability to create events in your system, and then maybe having either a cron job or an event or a queue-based system which just checks what webhooks to call every second maybe, and start dispatching those fetch requests to the endpoints. So yep, that's pretty much it for this video. I hope you understood something new, understood the basics of webhook. If you have been working with payments, I know you would know a bunch of these things already, but it's good that we take out some time to understand a few concepts in depth separately as well. That is all for this one. If you liked it, make sure you leave a like and subscribe to the channel. I'm gonna see you in the next video really soon. If you're still watching this video, make sure you comment down in the comment section, I watched this video till the end. Also, if you're not part of codedamn's Discord community, you're missing out a lot on events which we organize on a weekly basis to code. You already know the drill. Make sure you like the video, subscribe to the channel if you haven't already, and thank you so much for watching.